did another thing in this study as well. I added titanium. Let's look into the titanium. The addition of titanium does. When I added it, it formed two phases. The one which is stable SR4 and B4, O14. Why SR4 and B4 O14? Why not SR2 and B2 O7? This is associated with the independently stable number of atoms within the structure. Why people use that? And I found another phase, tungsten TTB, tungsten bronze structure. Tungsten bronze structure is a known structure within the crystallographer. So the one that is SR2 and B2O7, this is a atomic structure, and the other one, the second phase that forms because of titanium addition, its composition was this: SR3 and B4 TiO15, and it is tungsten bronze type structure. So the material became two phase, but you will be surprised to know this, the left hand side, it is the single phase material. It is the single phase material with strontium and niobium alone. I checked individual grains. I am not calling them crystals, although XRD has given me that these are crystalline phases, but I am not calling them crystals here. I am calling them grains. And those grains, when I told you yesterday that if this is a grain and I select this area and I measure the composition, I found these two peaks, which is strontium and niobium. But when I put that titanium in it, and I have seen that titanium peaks are also there. Right? That is why I am saying. But I found two types of peaks there. And I should expect that if I am having two phases here, right? But if the chemistry is quantitatively different, if I have in one phase more niobium and in other less niobium, it will not be easy to resolve contrast-wise. More niobium, less niobium. It will not be easy to resolve from each other, to distinguish between the two crystals with more or less niobium with backscattered electron microscopy. But if the composition is different, the element is different, quantity is the same, but the elemental cation is different, then some cation will give me brighter contrast in the backscattered imaging. Backscattered imaging is basically composition contrast. Backscattered imaging is basically composition contrast. Now, if I see that two phases are forming inside the material, the microstructure should also be different from that. If I am seeing single phase material here, I am seeing two types of contrast there. This variation in contrast, these whitenesses, these are because of the ups and downs on the surface of the sample. It is not because of the composition. But if you look there, that contrast is completely different. And only a scientist's eyes can distinguish between the two. For an ordinary person, this is also the same thing. But when you look into the color, it is ups and down within the sample. An electron beam goes down into the sample and then comes back. And it reflects from the top. Its contrast will be slightly different, right? But there, it is because of titanium. That in these grains, you don't have titanium. And though that microstructure, you have one phase, strontium niobate, and the other one with strontium niobium titanate. And because of that, it is giving you different contrast. Now, looking into these grains, and people say that the grain size was this much, you will have to measure the dimensions of many grains so that you can get a statistically defendable number when you report it. Because if somebody tells you that you have written that the grain is 10 micron long and 5 micron wide, for example, and he shows you a grain which is 1 micron long and half a micron wide, then he should fail you in your PhD and your MPhil and your publication should be rejected because you are not telling the truth. The safest statement is that I measured the particles. If you could average it to 5 and to 10, well done. But if you couldn't average it, one grain is 10 micron long and 5 micron wide, right? And the other is 0.1 micron length and 0.01 something wide, then the best statement is the grain size inside this sample ranged from approximately 0.1 into 0.01 micrometer square up to 10 into 5 micrometer square. So you covered all of them, and whoever asks you, you have the industry and you can show them that yes, this grain is this much. So that is the sound statement. Why you are saying something, that why must be defendable and you will be able to do it. Now I'm telling you that these are grains when we start to call them crystals. When you go to the transmission electron microscopy, then you call them crystals. That this DM image is from pure strontium niobate, and that image is with 0.67x. Both the diffraction pattern was solved almost with the that was solved on the tungsten bronze structure, and this one was solved on the orthorhombic strontium niobate structure. So you made the material, you processed the material, you did DTA the material before processing, then you looked into the constitution of phases inside the material, whether they are single or not, then you went to the density, people measure it, then you go to the microstructure, or the grains densely packed, they are scattered, the structure is contiguous, the structure is appear loose, the grain size is non-uniform, the grain size is uniform, grains are elongated, grains are needle-like, grains are lathe-like, grains are rectangular, grains are cubic, cuboidal, ellipsoids, spherical, spheroidal. There are right irregular shaped. If there is no name, irregular shape is there. But you must describe things. You will have to describe things. If you are publishing a paper, if you have processed a material, if you have studied the material for 5 years and you can't name it, you can't characterize it, who else do you expect to call it? No, you must be confident enough and you must have studied all the relevant literature that you fully describe the phases, the structures, the crystallography, the properties, and everything inside that material. Clear variation. These crystals are like this. But I told you that if you see one over the other like these, and you see only this face, it will appear as rods or needles. But if you see this face, it will appear as almost rectangular type. If they appear like squares, if they are like this, then all the shapes and things will be different, right? So always don't conclude your data only on your experience. Don't conclude your data only based on your own experience, but try your best to get the maximum information, because the one you are calling needles are plates and you are telling people that they are needles. So research is not something that you did it and that is the end of the world. No. The subject in which I did PhD, a person called Kinser, Kinser. He did his PhD in the same subject in 1968. And I did my PhD in the same subject in 97 or 96, say. Right? Then, in those days, he was head of department in my Haas department. He had done PhD in that subject somewhere in 74. Right? So this means still people are working on that material. So never think that I am the only one who just did it and it will be sealed somewhere in the locker. No. People will work on that material. Today something else will occur, tomorrow something, the application will change, right? All things are changing. So whatever you conclude, it number one must be based on your repeated experiments. Secondly, in light of the previous literature, if you are contradicting the results of the previous literature, if you are contradicting the results of the previous literature, then there must be a solid reason for that. There must be a solid reason for that. If you are agreeing, then it is not a big problem, because you are supporting him and he is supporting you. But if you are contradicting, he says that a monoclinic structure forms and you say it's not monoclinic, then you will have to make your statement very sound and very well supported by experimental and different evidences. But what strange I found in this material, so I told you that in the first case, I just made the formula SR4 NP4 O14 and Y, and SrClO3. So when I was putting more titanium in it, I was equally getting strontium as well. This gives you another clue that you are changing two variables at a time, right? You are changing two variables at a time. One is enhancing the property, for example, and the other is compensating for the loss you will incur because of that substitution. So you are making things complex to get more properties. On the one hand, you are enhancing one property, but it is compromising the other property. And you make another addition which is compensating the next property. And in this way, you are optimizing the structure, the properties, the processing, and different things. If I remove this strontium and I only add titanium, then I told you that the material became diphasic, two-phase material. Now one phase will have one type of properties, the other will have other type of properties. For that reason, you will have to proportionally think of the properties. If 55% of the material had the dielectric constant 50 and the 45% of the material had 100, then your total dielectric constant is 45 into 100 plus 45% into 100 and 55% into 50. So you can quantify your properties as well.